Black holes are supposed to be silent killers of the universe. When two of them collide, the event is unimaginably violent, but strangely invisible. No flash of light, no explosion, nothing telescopes can see. Only faint ripples in space-time race across the cosmos. But in November 2024, something happened that left astronomers completely stunned. Instruments on Earth detected the unmistakable signal of two black holes smashing together billions of light years away. And then, just seconds later, space telescopes spotted a powerful flash of gamma rays coming from the exact same region of the sky. That shouldn't be possible. Black hole mergers aren't supposed to produce light at all. Yet the event, now known as S241125N, appeared to do exactly that. And if what scientists witnessed is real, it could mean that one of the universe's most mysterious events might not be as invisible as we once believed. But to understand why this discovery has researchers so puzzled, we first need to look at how the collision itself was detected. The first clue arrived as a faint ripple moving through space-time itself. Deep beneath the noise of the universe, a network of ultra-sensitive detectors suddenly picked up a signal unlike anything produced on Earth. Observatories including LIGO, Virgo collaboration, and KAGRA had captured the unmistakable signature of two black holes spiraling toward each other before finally colliding in a catastrophic merger. The signal revealed something astonishing. This wasn't just another routine detection. It came from about 4.2 billion light-years away, meaning the collision happened long before life on Earth had even begun to evolve into complex forms. And the objects involved were enormous. Together, the two black holes weighed more than 100 times the mass of our Sun, placing the event among the most massive stellar black hole mergers ever observed. For scientists studying gravitational waves, signals like this are incredibly valuable, but they usually come with one frustrating limitation. Black hole mergers happen in near-perfect darkness. No light, no explosion, nothing visible to telescopes. Normally, once the gravitational wave signal fades, the story ends there. But this time, the universe had something very different planned. Just seconds after the detectors recorded the collision, another instrument watching the sky picked up a signal no one expected to see. Just 11 seconds after the merger signal arrived, another alert appeared, this time from space. NASA's Neil Gehrels Swift Observatory had detected a sudden gamma ray burst, one of the most energetic types of explosions known in the universe. These bursts release enormous amounts of radiation in just a fraction of a second, often outshining entire galaxies during their brief flash. But here's the problem. Events like this are almost never linked to black hole mergers. Short gamma ray bursts are typically created when two neutron stars collide, not when black holes crash together. At first, scientists assumed the timing was just a coincidence, but then another piece of evidence appeared. Not long after the gamma ray burst, the Chinese space mission Einstein probe detected a possible X-ray afterglow coming from the same region of the sky. Suddenly, the coincidence started to look much less random. Two completely different types of cosmic signals, gravitational waves and a burst of high-energy radiation, both pointing to the same patch of space. That raised a question researchers had never seriously considered before. Could a black hole collision actually produce light? But when scientists examined the radiation more closely, the mystery only deepened. When scientists began analyzing the gamma ray burst in detail, they noticed something strange, almost immediately. The radiation didn't behave like a typical short gamma ray burst. Usually, these bursts release extremely energetic photons right from the start. But in this case, the initial flash detected by the Neil Gehrels Swift Observatory appeared softer than expected, meaning the photons carried less energy than what astronomers normally see in these kinds of explosions. Even more puzzling, the afterglow detected later seemed unusually intense, almost the opposite of what researchers typically observe. This unusual combination suggested that whatever created the burst might be very different from the neutron star collisions that usually produce gamma ray bursts. That realization pushed scientists to run detailed statistical tests comparing the gravitational wave signal with the gamma ray data. The results were intriguing. According to their analysis, the odds that these two signals just randomly appeared in the same place and time were extremely small, roughly one false coincidence in about 30 years of observations. Even with those numbers, researchers remain cautious. The connection isn't proven yet, but if the signals really did come from the same event, it would mean something extraordinary happened during that black hole merger. And to explain how such an impossible flash of light could occur, scientists began exploring one of the most extreme environments in the universe: To explain the impossible flash, scientists began looking at a place where black hole mergers might not happen in empty space at all: the chaotic centers of active galaxies. At the heart of many galaxies lies a supermassive black hole surrounded by a blazing whirlpool of gas and dust known as an active galactic nucleus. Inside this enormous disk, matter spirals inward at incredible speeds, heating up and releasing huge amounts of energy. But these disks may contain more than just gas. Researchers believe they can also trap smaller black holes drifting through the galaxy. Over time, these wandering objects could become embedded in the dense material, slowly migrating through the disk until some of them pair up and form binary systems. Eventually, those pairs would spiral together and collide, right inside this thick, turbulent environment. If the event known as S241125N happened inside such a disk, the merger wouldn't occur in darkness. Instead of empty space, the newly formed black hole would suddenly find itself surrounded by enormous amounts of gas and debris. And that dense cosmic fuel could completely change what happens next. Because when black holes collide in a place like this, the aftermath might be far more explosive than anyone expected. When two black holes finally merge, the event doesn't always end quietly. In many cases, the newly formed black hole receives what scientists call a recoil kick, a powerful shove caused by uneven gravitational waves blasting out during the collision. This kick can launch the newborn black hole through space at incredible speeds, sometimes thousands of kilometers per second. If S241125N happened inside a dense galactic disk, that recoil would send the black hole racing straight through thick clouds of gas and dust. And as it tears through that material, something dramatic could begin to happen. The black hole would start pulling in surrounding gas at an extreme rate, swallowing huge amounts of matter far faster than normal. When this much material spirals toward a black hole, the energy involved can ignite powerful relativistic jets, narrow streams of particles and radiation launched from near the black hole's poles at nearly the speed of light. But inside a dense disk, those jets wouldn't immediately escape into space. Instead, they could remain buried deep inside the surrounding material, pushing outward and building enormous pressure. For a while, the energy would stay trapped, hidden beneath layers of gas. But eventually, that pressure would have to go somewhere. And when it finally breaks free, the result could be a sudden burst powerful enough to light up the universe. As the hidden jet continues forcing its way through the dense gas of the surrounding disk, enormous amounts of energy begin to build up inside the material. The jet acts like a cosmic drill, pushing outward while powerful shockwaves race through the gas around it. For a time, all of that energy remains trapped beneath the thick layers of the disk, unable to escape into space. But eventually, the pressure becomes too great. When the jet finally punches through the surface of the disk, everything changes in an instant. The energy that had been building up suddenly bursts outward in what scientists call a shock breakout, a rapid release of radiation powerful enough to produce a brief but intense flash across the universe. That sudden eruption could explain the gamma-ray burst detected by the Neil Gehrels Swift Observatory. And because the radiation had to fight its way through dense material before escaping, the signal would appear slightly different from typical bursts, softer at first, with unusual energy patterns that match what astronomers actually observed. If this scenario is correct, the mysterious flash wasn't a coincidence at all. It may have been the moment when a hidden jet from a black hole merger finally broke free from its cosmic prison, sending a brief signal across billions of light years. But if that interpretation is right, the implications for astronomy could be enormous. If future observations confirm that the gravitational waves and the gamma-ray burst truly came from the same event, the discovery could change how scientists study some of the most powerful phenomena in the universe. Until now, black hole mergers have only been detected through the faint ripples they send through spacetime, signals captured by observatories like LIGO and Virgo collaboration. Telescopes searching for visible light usually find nothing at all. But if events like S241125N can also produce radiation under the right conditions, astronomers may have an entirely new way to investigate these cosmic collisions. Detecting both gravitational waves and light from the same event would open the door to a powerful field known as multi-messenger astronomy, where different signals are combined to reveal far more about what's happening in distant galaxies. It could also help explain how some stellar black holes grow to enormous sizes. If mergers occur inside the dense disks surrounding supermassive black holes, repeated collisions in these environments could gradually build heavier and heavier objects over time. For now, scientists are still cautious. The connection between the signals hasn't been fully proven, and more observations will be needed before anyone can say for certain what happened 4.2 billion light-years away. But one thing is clear. If this mysterious flash really did come from a black hole merger, it suggests that even the darkest objects in the universe might occasionally leave behind a burst of light powerful enough for us to see across the cosmos.